Hi, my name is Thomas, and together with Xander, we will be presenting our work OPTIMSM. This is a joint work with Jonas, Wouter, Michiel, and Ingrid. And OPTIMSM is a FPGA hardware accelerator for a multi-scalar multiplication, or MSM for short. So first, why are we accelerating this building block? Well, this is because the multi-scalar multiplication is typically the bottleneck in ZK snarks. ZK snarks are a type of zero-knowledge proof, and the MSM in this proof generation time takes over 70% of the time. So if we can accelerate the MSM, we can accelerate zero-knowledge proofs. A multi-scalar multiplication is defined as given a list of elliptic curve points and a list of scalars to take the inner product between the two lists and then to sum all of those results together. Because we are working over elliptic curve points, the elliptic curve addition is our basic building block, our basic operation, and this one is in itself composed of many modular multiplication, which makes the whole thing computation bounded. If we can reduce the number of elliptic curve additions that we need to compute, we will also in turn reduce the time for the multi-scalar multiplication directly. The MSM is typically computed using the Pippenger's algorithm, so we will first give some intuition to what this algorithm does. And Pippenger found out that instead of first multiplying every point by the corresponding scalar, it is advantageous to first accumulate all of the points that have to be multiplied with the same scalar and only then do the multiplication by z scalar. So in our example here, we can first accumulate all of the points that need to be multiplied with the scalar 1 in a so-called bucket 1, all of the points that have to be multiplied by 2 in a bucket 2, and so on. And then only in the second step, we do the multiplication of those storage elements by their index, and we find the result for the total multi-scalar multiplication. This was a toy example with scalars only up to the value 3, but in realistic cases, the scalars are b bits long. And this means that we will first need to split up the scalars into smaller parts and then do this accumulation of the same scalars for each of those windows separately. Because that is what we will call this group of scalars. This is a window that we will put all of the points into one window and then corresponding to the second set of subscalars into the second window and so on. The second step then takes all of these windows separately and computes the second step, the aggregation on each of them in sequence. The important trade-off parameter for the Pippenger algorithm is the window size, C, in this implementation. And this will determine how many elliptic curve additions will be done to compute the Pippenger algorithm. If we increase C, the window size gets bigger, so we will have fewer windows for the same scalar, so the accumulation step will be cheaper. However, as we are increasing C, we are pushing more work to the aggregation step, so this step will be exponentially more expensive. There are a few optimizations already known in literature over the Pippenger algorithm, and we will cover 3 of them that we have combined together in our work. The first one is the signed digit representation, which exploits a property of elliptic curve points that the negative of a point is very cheap to compute by just inverting the y coordinate. So we can exploit this to make our windows smaller. We will have less buckets in every window, because if we have a most significant digit of 1, we can reinterpret, for example here, 39 as 64 minus 25. The 64 we can add as a 1 into the next window, and the minus 25 is our new subscalar. So instead of adding point P0 into bucket number 39, we will now add minus P0, the negative of P0, into bucket number 25. And this way, if we do this for all of these subscalars, we will find that we only need half of these buckets, because the largest scalar that is left will be 2 to the power c minus 1. Because we can save here buckets, all of the aggregation steps will be cheaper to compute, and also we need fewer storage elements to save all of these accumulation results. The second optimization also makes use of a property of elliptic curves, namely the efficiently computable endomorphism. And this property says that if you have an elliptic curve point P, you can cheaply compute lambda times P with lambda, a scalar that is a constant for the curve. And this optimization will allow us to split every scalar into two parts that are more or less half of the size of the initial scalar, and then have double the amount of points, the points and the endomorphisms of the point that need to be put in the buckets. But as we are now using scalars that are only half of the size of the initial scalar, we will have about half as many windows. So instead of having twice as many windows, we are once again saving storage space for all of these buckets, and also we only need to compute this aggregation step for the remaining windows. And this all comes at the cost of this one modular multiplication to compute the endomorphism of the points on the fly. The third optimization has a quite similar approach, but it uses pre-computation and is the so-called BGMW method. This one will also reduce the number of windows, but instead of only halving it, it will be able to reduce the number of windows to 1. We can use pre-computation because the elliptic curve points are constant over many different computations of multi-scalar multiplications, so we can pre-compute on them and store and use these results. So what will we pre-compute here? Well, for every point, we will pre-compute 2 to the power c pi, 2 to the power 2c pi, and so on. And then instead of putting the points p into every window according to their scalar for every window, now for the second window, we can add pre-computed points into the same window. Once again, this saves us storage space because we don't need all of these buckets anymore, and we now only need one aggregation step. What this does cost us is off-chip storage to store all of these pre-computed points and bandwidth because we need to put them onto the device at runtime. Okay, this was all literature, so now let's start combining them. And first we can explain how we combined the SDR, the signed digit representation, and the pre-computation. This is quite straightforward as they don't really interact with each other. You just simply get half of the number of buckets per window and you have only one window left. However, this pre-computation that we talked about before takes n times the number of windows pre-computed points. And this is rather large, and in our paper we suggest combining this with the endomorphism to reduce this number of pre-computed points by half. How we do this is by first applying the endomorphism so that we are left with b over 2 bit scalars, so that we need fewer pre-computed points to be able to put everything into one window. So therefore, we need fewer on-chip storage and bandwidth, but we again need this one modular multiplication to compute the endomorphism on the fly. If we now look at what we were doing, we wanted as little elliptic curve point additions for one multi-scalar multiplication as possible. Then we can first look at the figure on the right, where none of these applications were applied yet. And there we see that if you're increasing the window size, first the number of elliptic curve point additions drops, but later we see an exponential rise as the aggregation starts to kick in. The drop, in the initial drop, is that the fact that the accumulation steps get cheaper as you increase the window size. However, if you look at this graph, we want to be here somewhere around a window size of 20 bits, but this is not possible because we are restrained by the number of on-chip memory elements. And for implementation on FPGA, this limits us to a window size of around 12 bits. This means that we are in a point, a suboptimal point on our curve, and that is why we combined all of these optimizations to be able to go to larger window sizes. If we now give the graph here with the new on-chip memory requirements with all of these optimizations, we can see that from 12-bit windows we can go to 17-bit windows, which pushes our allowed region to go further, giving us a quite significant increase in the number of elliptic curve additions for one multi-scalar multiplication. Moreover, as you saw, the curve now only takes this exponential behavior for larger window sizes because this aggregation step throughout the optimizations has become cheaper. However, 17 is still not what we want. We would realistically now want to go to even larger window sizes, and that is why we figured out a way to reuse on-chip memory with an approach we call the Iterative Multi-Scalar Multiplication. And we want to reuse on-chip memory so that we can go to larger window sizes, and to be able to do that, we split the multi-scalar multiplication up into multiple independent iterations. Previously, we had scalars between 1 and 2 to the power c minus 1 because of sign-digit representation, but now we only want 2 to the power c minus 3, for example, different scalars. So how can we do that? Well, we will just select the scalars based on their uppermost, the most significant bits, and only handle those subscalars and those points in every iteration. If the subscalar is indicating that it belongs to another iteration, we will just simply drop it and forget about it in this iteration. Another iteration will handle it. In our paper and in this presentation, we give an example of 4 iterations, but you can go to larger and to even more iterations, but there is a constraint on the memory bandwidth. And to be able to understand that is to look at the iterations and see that in every iteration, we're only keeping 1/4 of the total computations that we need to do in this iteration. The other 3/4 we're just dropping, so we need to make sure that the memory bandwidth is sufficiently high so we can put the points, the pre-computed points, and also the scalars quick enough on the FPGA to make sure that our elliptic curve adder will be kept busy. We did all of this to be able to go to larger window sizes, so that's also what we achieved. Instead of 17-bit windows, we can now go to 19-bit windows, which allows us to push the allowed region a bit further. This was an example with 4 iterations. You can go to larger iterations. You just need to make sure that you can keep the elliptic curve adder constantly busy. As we've now already seen the theory behind our implementation on the FPGA, we can go to some theoretical results where we can see that we implemented a window size of 19 bits, resulting in 14 different windows. This is the largest implemented on FPGA yet, and all of these optimizations result in fewer elliptic curve additions to compute 1 MSM. Other implementations on FPGA get these 12, maybe 13-bit windows, as we discussed earlier. This one other paper here, the LFG23, is a CPU paper that also achieved a window size of 19 bits, but optimizations that they suggest require way more off-chip memory, so we cannot put all of the pre-computed points in DRAM anymore, so therefore we needed to look at other optimizations. This was the more theoretical perspective. Now we will look at some hardware aspects of the implementation.
Thank you, Thomas. So let's now go to the hardware implementation. So whenever we start implementing this multi-scalar multiplication, we start with the elliptic curve adder, and then it will mostly look like this, where we have our elliptic curve adder connected to some memory where the buckets are stored, and then we have a queue where the points will be stored and then fetched whenever we want to do an addition. However, when we start implementing this elliptic curve adder, we always implement it fully pipelined, which means that we can start every cycle we can start a new elliptic curve addition. However, it takes a certain number of cycles before the addition is done. And this means something new occurs that is called bucket collisions. So what happens is that every cycle we start a new addition, a new point is fetched from the queue. However, at a certain point, it can happen that the next point that is fetched wants to be added to a bucket that is currently computed on in the pipeline. And at this point, we cannot do anything. We have to stall the pipeline. We have to wait until that computation is done. And this means we are losing cycles. And so with this simple design, you can prove using Markov chains that you will lose around 11% of the total cycles, which is quite a lot. And that is why in literature there exists other types of schedulers. For example, a scheduler from Cyclone MSM, which is called the delayed scheduler. It uses 2 different kinds of queues and a collision detector. And what happens is that whenever a collision is detected, it will put that colliding point in a second queue. And then it can still fetch from the first queue and go further. So you only lose one cycle. And at the end, when the queue is empty, you just go to the second queue and just start again. So this scheduler only loses around 0.2% of the total cycles, which is quite an improvement compared to the simple design. However, there are quite some complexities to design this in hardware. For example, what length should the length of Q2 be? Because in the worst case, almost all points are colliding and they have to be stored in Q2. So you cannot make it as big as you want. What happens when it's full? Do you then wait? Do you go to the Q2 again? So this is a bit more complex. That is why in our hardware implementation, we try to keep it simple and have multiple queues in parallel. So here we just fetch multiple points at the same time. We put them in separate queues. And when we start fetching points from the queues, we just start fetching from Q1. And whenever a collision happens, we just start fetching from Q2 instead. Of course, it can happen that in both queues there is a colliding point. Okay, then we are stalling the pipeline, unfortunately. But with this more simple design, you can prove also with Markov chains that you lose around 0.7% of the total cycles, which is a bit more than the delay scheduler, but it's much more simple to implement in hardware. You can even extend this idea to more queues. For example, 3 queues will only lose you 0.03% of the total cycles. So we took this scheduler design and put it in our whole hardware implementation that looks like this. So this is all implemented on FPGA. Our points and scalars are stored in memory. They're then fetched by our interface. And we have then 7 points that are then stored in the FIFOs. Remember, we are using window sizes of 19 bits, giving us 14 windows in total. But because we have an endomorphism, we only need 7 windows per scalar. So when the points are then stored, we can do the scalar preparation step, which will calculate from the bigger scalar the 2 smaller scalars, such that we can use the endomorphism property. And then we do the signed digit representation optimization to get 14 smaller scalars, where each smaller scalar also has a negative flag, indicating whether or not we have to take the negative of the elliptic curve point. Then the 7 points and all the subscalars go to the point selection module, and this is the point where we implemented our iterative MSM technique. And here we will select, depending on the scalar that is coming in, do we need to, in this iteration, do we need this point or not? If we don't need this point, we just throw it away. We don't store it in the next FIFO. Then we have 7 FIFOs in parallel, each having their point and their scalar. However, our collision detector only wants 2, so we have this queue selection module in between that goes from 7 to 2 queues. And then when we have 2 queues, we can use our queue scheduler method to fetch queues to minimize collisions. Then whenever a point is fetched, we start the point preparation module, where we then calculate the endomorphism of the point and the negative of the point. Because these 2 optimizations act on a different coordinate of the point, we can do these things also in parallel. And then we do the elliptic curve addition. It's added to a bucket. The whole process accumulates. Then we do the aggregation step. At the end, we get 1 result for each iteration, which is then sent back to software to calculate the final result. So this is all implemented on a U55C FPGA. Running at 260 megahertz. We have 2 different designs, one on 1 FPGA running the 4 iterations sequentially, and one having 4 FPGAs where each FPGA is running an iteration in parallel. And so implementing this, we can do an MSM of size 2 to the power 24 in less than a second, or if you use 4 FPGAs in 200 milliseconds. And this, if we compare to other FPGA papers, is a speed up between 2.7 up to 12 times better. So to conclude, in our paper, we combined the signed digit representation with the BGMW method, but also shown that you can still use the endomorphism property in hardware to effectively reduce the amount of off-chip memory you need and also the bandwidth that you need. We then proposed an iterative MSM technique, a way to reuse on-chip memory to effectively push for larger window sizes and get improved latency. And by doing all this, we achieved a window size of 19 bits, which is the largest FPGA implemented window size. If we then compare, for example, as Thomas said, to a CPU paper that has the same number of elliptic curve additions, we need 6 times less off-chip memory. And so at the end, we implemented it on an FPGA and can run an MSM of size 2 to the power 24 in around 200 milliseconds. So thank you for listening, and we're happy to answer any questions.